science. So what I'll be presenting to you today is my first ever research project that I did last year, so it's hot off the press. And it's all to do with the plasticity of escape responses in coral reef fish. Now, just to give everyone a sort of background view of what's happening here, we want to talk about predator-prey interactions. Now, most of us would know these interactions occur all around the world. We see it in terrestrial environments with lions, zebras, spiders eating insects. Even it happens in the oceans, where you've got sharks just breaching out of the water, and it's quite impressive. Now, these interactions play major roles in determining the life history characteristics of a certain population. And that's by putting strong selective pressures upon that populations. And these pressures then cause shifts in the phenotypes that alter the gene frequency to what we see in the individuals today. Now, predator-prey interactions follow a short schematic. So if you just want to follow with me here, we've got predators on one side and the prey on the other. After encountering each other, both these individuals then have to detect and identify each other. I want to talk about prey. So how do these prey individuals identify their potential predators? Now, firstly, they can use their sense of hearing. They can hear their predators around them. They can also feel them using their mechanoreception with their lateral line. They can see them, but in a topographically complex environment, that is a coral reef, where you've got corals all around and it's hard for an individual to see past it, one of the most important senses for these fish is that of their sense of smell. And there's so many chemical cues that float around in the water all day, and these fish have to identify and learn what these smells are. How do they do it? So just follow these fish here. Imagine a school of fish on a bright sunny day. One of them happens to swim a bit too far, and then he becomes lunch. Now, when these predators attack the fish, what happens is they damage the outermost surface of their epidermis, and that releases what we call chemical alarm cues. Now, these chemical alarm cues elicit natural fright responses in conspecific fish. Now, these chemical alarm cues, coupled with the scent of the predator, flow downstream. And these fish can then learn that that predator is scary. So when they float downstream, these fish learn that's scary and they avoid that predator for the rest of their lives to keep safe. Now, it's all well and good to learn, but what happens when you're out on a reef? There's all these things you have to do to promote your fitness. You have to eat, you have to look for shelter, you have to find a mate. So these fish have to think and kind of weigh up their risk that's around them and make a good decision based on their experiences. So let's take a nice reef, whole bunch of fish swimming around, and then a predator turns up. Now, some of these fish decide, okay, I'm not going to take the risk. I don't feel like being eaten today. I'm going to hide. Now, these fish are then stopping, feeding. They're not looking for shelter, so there's that trade-off. These other few that are happily eating, they then have to make the decision to escape at the right time. Now, if you make the decision too late, you become lunch. That's the end of you. No mating for you in the future, which is a bad thing. So this is what I want to talk about today, are these escape responses. But before I go into that, let's go back to our encounter. So our predator on one side, our prey on the other. When that predator decides to attack, it elicits what we call an escape response. Now, this can lead to either capture of that prey individual or a successful escape and living for another day. All right, fast starts, otherwise known as escape responses, are short, high-energy swimming bursts powered by the anaerobic system. Now, that video I had there that's not playing, for some reason it was working this morning, it's a fish that was swimming away from a stimulus. Now, these fast starts comprise of many variables, such as responsiveness, their reaction distance, their latency, which is the time taken for that individual fish to react to a stimulus, and their propulsive performance, so their swim speeds, so on and so forth. Now, it's important to note there's a high degree of variability within and between individuals of certain species. And this points to sort of the cognitive ability. Why do these fish need to think about needing to escape from danger? That's because there is a debt to pay. As I said, these fast starts are powered by the anaerobic system, so there is an oxygen debt to pay later on. So they're not always going to want to put all their energy in. So this is where I come along. And the aims I had for this study was to see if recent experience of predator cues affect the escape responses of juvenile coral reef fish, and to take it one step further, how the olfactory and visual information that these fish take in inform that escape response. So I, like many lucky individuals in our marine science community, got to go up to Lizard Island and do some science. What I used was the Spinochromis, Acanthochromis polyacanthus, as my study species. I went out into the reef and caught them using hand nets. I then brought all these little fish back into my aquarium, back into my lab, and I taught all my fish what a predator was. So I used the sight of the predator in a plastic bag, an empty bag, their odor, and injected that chemical alarm cue. Now, just to reiterate, putting that chemical alarm cue with those predatory cues allows an individual to associate that predator as dangerous. Okay, so all my fish had that same base learning. From there, individual fish were put into one of 4 treatments. I had my control treatment, which was just an empty bag of salt water with a saltwater injection. A chemical treatment, which was the chemical alarm, the predator odor with an empty bag. The visual treatment was the predator in a bag with a saltwater injection, and a combination of both those predatory cues, that being predator in the bag and the predator odor injection. So for my little fast start arena, I had my fish in these little tanks, and then I had a stimulus weight that was held up by an electromagnet. Once that fish reached that middle of the tank, which would give it an equal opportunity to swim off to all areas of that tank, I would then put in some cues. So in this case, I'm using my combination cue where I've got the predator in a bag and their odor injected. Once the fish is ready, I turn off that electromagnet, which dropped that stimulus weight into the water, which elicited that fast start response. Now, all these responses were filmed at high speed using a camera pointed at a mirror, angled at 45 degrees, that gave me an underside view of the fish, so the fish didn't know I was there, which is pretty cool. As I said, all these responses were filmed at high speed at 420 frames per second, and that gave me a very high resolution to kind of tease apart what was happening. And the variables I'll be talking to you guys about today were the latency, so that is how quick that fish reacted to the stimulus, how far they swam away, and their maximum speed during the response, and their maximum acceleration. Just a little bit of statistical stuff that I did. I used a MANOVA to start it all off, and then used individual ANOVAs to find out any differences I found. Now, with the first graph over here, I've got my control in the green bar and all my predator cues in the right. And what we can see straight away, that once these fish know they're in danger, and if there's some sort of predator cue around them, they ramp up their response, so they respond quicker. And we can see if we tease apart the individual predatory cues, with the odor, they respond just a little bit slower than visual, we respond just a little bit slower than the combination. So there seems to be a sort of additive effect there, though it wasn't significant. If we look into how far they swam away, we once again see, once they know there's danger around, they want to get out of there. So these fish swim away further than those individuals that had no sort of predatory cue around them, which meant they were safe. When we look into their maximum response speed, once again, a little additive effect. The controls don't swim away too quick, but those that have the chemical odor of that predator in, they ramp it up. Those that can see the predator, ramp it up even more. If you have both, you're getting away from there as quick as you can. And lastly, you can see that in the acceleration as well. Once again, all our predator cues are ramping up their response because they know they're in danger. So just to summarize my results here, we can see that fish conditioned to predator cues increase their responsiveness. So not only do they respond faster, they swim away further, and they swim away faster as well. Now, what does this all tell us? All in all, we now know that exposure to these predatory cues and prior learning helps these fish increase their responsiveness, both in sensory systems, which we've seen in latency, and their locomotory systems, which we've seen in the distance they've traveled and the speeds they increase when they get that stimulation. So this kind of points to an increased vigilance. We know now that these fish were probably ready and waiting. They got those cues, and they were just waiting for that little stimulus to make them go, all right, let's get out of here. So their latency was affected. And we also see their locomotory abilities increase. These fish understood the risk associated with not getting away. If they don't get away quick enough, they're lunched. They're not around for the next day, the day after that. So we now know there's a great behavioral component towards this fast start escape response than previously assumed. A fish running away, or sorry, swimming away from danger, isn't just going to put all its energy in because it's in danger. It's going to think, how much danger am I in? Do I need to use all my resources to be able to react? So we know now that they can optimize their responses based on their perceived level of threat. Now, just a few people I need to thank before I go. I'd like to thank my supervisor, Mark McCormick, my amazing mentor, Brady Allen, who kind of held my hand when times got rough sometimes. My whole lab group that came up to Lizard Island with me and kind of spent 7 weeks with me. And especially my volunteer, Rachel Woods, who had to put up with me in the lab when I had really annoying jokes. And obviously I have to thank the Centre for giving me the funding and giving me the opportunity to kind of start my research career. Now, what I've shown you today is just a little scratch in the paper that was published last year. So if you'd like a little bit more information, check out this amazing paper. If you want to have a chat with me later on, come up and feel free to have a chat. Once again, thank you very much for the opportunity to present.